everyone. Happy Valentine's Day to all of you. Just for fun, here is the hormone oxytocin, which is associated with feelings of love and connectedness, or not, I don't know. You'll notice that this molecule probably looks similar to something you saw on a test, in the sense that this is a peptide. It's got a backbone that consists of carbons, nitrogens, and oxygens connected by amide bonds. So this is sort of the peptide backbone, and you've got side chains linking off of it. Anyway, kind of fun. Notice actually, if you look at all of these, that none of the side chains are charged. The most polar side chains you have are these amide groups, but those don't have pKa's that are relevant at physiological pH. So this molecule is neutral at physiological pH, which is important for it binding its receptor and trafficking through membranes and so on. Anyway, there you go. Love and organic chemistry. Moving on, we were talking about how to know whether a reaction is favorable or not. This is why reactions happen. And the reason why reactions happen is that the bonds you form are more stable than the bonds you break. If that's not the case, the reaction's probably not favorable, and you'll have to take other steps to make it that way. For example, using Le Chatelier's principle. But we gave you an example of this. This is a substitution reaction because we end up swapping out a chloride group for an OH group. And the bonds we formed, as we discovered last time, the carbon-oxygen bond and the hydrogen-chloride bond together are more stable than the bonds you break, which are the carbon-chloride bond and the oxygen-hydrogen bond. And we can figure that out by using the appropriate bond dissociation enthalpies that you can get from a table in your text or from the appendix at the end, and end up with the prediction that this is favorable, at least in terms of enthalpy, by about 3 kilojoules per mole. It's not a huge amount, but it is downhill. I will point out that, like we said last time, enthalpy isn't the only thing going on in whether a reaction's favorable or not. You've got enthalpy and entropy. For the most part, we're going to assume that entropy changes are small for these organic reactions, though I pointed out a few situations last time where that isn't the case. All right, one last sort of thing on this subject of bonds being broken versus formed, and what energy is released in a reaction. You won't like this, but I guess I don't care. This molecule is called glucose. I'm drawing it for you in its chair conformation. And glucose reacts with ATP in the first step of glycolysis to give you glucose 6-phosphate. Glucose 6-phosphate, and of course ADP. Now I'll draw the structure of ATP for you. I realize that in doing so I run a risk because at least some of you are going to ask, do we have to memorize the structure of ATP? Not necessarily big on you guys memorizing structures. I'll try to be clear when I tell you that. So no, don't bother memorizing the structure of ATP unless you want to. But I'll draw it for you real quickly because it's going to illustrate a point and hopefully will help dispel a notion that we can sometimes pick up when people teach us chemistry and biology but use sort of shorthand to do it. All right, so this is the adenine part of ATP. This is the ribose part of ATP, and we're going to get to the triphosphate part of ATP now. ATP stands for adenosine triphosphate. Oops, that's not right. There we go. And we need a third. Okay, so that's ATP. In this reaction, we transfer this phosphate group onto the oxygen of glucose. And in all of this, we actually also need a water molecule, and then we need it to pick up a proton, basically remove the proton from the alcohol of glucose. I showed you, let's see, after the reaction we get ADP, which is over here, and to do that I need to erase the terminal phosphate group. All right, diphosphate, triphosphate, got it? So if you look at the bonds that are changing in this reaction, I'll try to illustrate with blue bonds that are broken. So an oxygen-hydrogen bond is broken. And then an oxygen-phosphorus bond is broken. Sorry, struggling with the colors. What bonds are made? Let's use red for that. We're going to make this oxygen-phosphorus bond, and I guess we need to draw out the structure of hydronium. We make this new oxygen-hydrogen bond. Overall, this process is really favorable. Downhill in energy, delta G is minus 17.8 kilojoules per mole. That's downhill in energy enough that this reaction is essentially irreversible. This is the first step of glycolysis, and you commit a glucose molecule to the downstream pathway when you do this. Why is this reaction favorable? Well, it's favorable because the bonds that you break, the OH bond and the O phosphorus bond, must be weaker than the bonds you make, which is another OH bond and another O phosphorus bond. Why that's true isn't necessarily obvious to you at this point, and it won't necessarily be until you take 352. Just as a preview, the bond up here is a weak phosphoanhydride bond. You're going to learn some things about anhydrides in 352, but that bond is weaker than this bond, which is a stronger phosphoester bond. You'll learn some stuff about anhydrides and esters in 352. You'll learn that anhydrides are less stable and or more reactive than esters are. And so that'll be sort of the explanation for why these bonds are more stable that we formed down here. But the point is that it's not breaking of the phosphate bond in ATP that releases energy, which is somehow in shorthand sometimes what people tell you when you're in biology class. Oh yeah, hydrolyzing ATP is great. You break the bond between the phosphate group and the other one, and then that releases energy. No. Bond breaking always requires energy to be put in. The thing that releases energy is if the bonds you make are more stable than the bonds you break. All right. I feel like I'm being kind of nitpicky on that one. I feel like one does not say that bond breaking releases energy. But anyway, that's sort of important, and it's important that you understand that. All right, that's thermodynamics. Now, we need to get to kinetics, which is another word which I think strikes fear into your hearts, because last time you were dealing with kinetics, I know this because I have a son in 106 right now, you were doing exponential decay laws and integrated rate expressions and things like that. We're not really going to do any of that, okay? We're going to write rate laws where we describe how the rate of a reaction depends on the concentration of various starting materials. But in organic chemistry, kinetics is really about two things. First, how fast does the reaction happen? But even at a more fundamental level, in what order a reaction involves bonds breaking and forming, in what order are the bonds broken/formed. And we're going to illustrate this issue with some reactions from chapters 7 and 8, mostly from chapter 7. So I told you that chapter 6 was going to bleed into chapter 7. We're going to talk about some issues from chapter 6 using reactions from chapter 7, and we'll be a little bit more efficient that way than we could otherwise be. So I'm going to show you a reaction from chapter 7. This is a substitution reaction, and we're going to discuss various mechanistic possibilities. And we'll also talk about how you might tell which of those mechanistic hypotheses or possibilities might fit in a given situation. So here is a starting material. I will go ahead and tell you that this molecule is a nucleophile. One way to tell it's a nucleophile is to notice that it's got a lone pair with a negative charge associated on it. I can go ahead and draw for you the whole structure of CN minus. But it's reactive at the negatively charged carbon, and the HOMO is the lone pair electrons on carbon. I know that because nitrogen, there are lone pairs on nitrogen, but nitrogen's more electronegative than carbon, and electronegativity literally means that electrons on a more electronegative atom are lower in energy than they would be on a less electronegative atom. So it just stands to reason that the lone pair on carbon is higher in energy and more reactive than the lone pair on nitrogen. All right, and then here is an electrophile. Because Lewis acids or electrophiles are electron poor, we care about what the lowest unoccupied molecular orbital is. This would be the carbon iodide sigma star, the antibonding orbital. All right, so we've done some of this thinking before, but the reaction here that happens is a substitution reaction. That substitution is a word that describes what? Which bonds are broken, which bonds are formed. In a substitution reaction, we break the bond between carbon and iodide, and we'll call this group iodide. We're going to call it a leaving group. That's just a way of describing what happens in the substitution reaction, because we're going to make a new bond between carbon and the nucleophile, and we're going to break the bond between carbon and the leaving group, and the leaving group's going to take the electrons that were in that carbon leaving group bond, and it's going to leave, which is why it's called the leaving group, right? Okay. So this is a substitution reaction. The nucleophile replaces the leaving group. Now, we could predict, based on bond dissociation energies, what the equilibrium constant for this reaction is. We won't do the math. I will just tell you that this reaction is very favorable. Equilibrium constant is much greater than 1. Delta G is much less than 0. So formation of products is favored. We will also, generally in organic chemistry, I don't know why it is, but you'll hear me use this term. We will call these reactants starting materials. It's a more wordy way of saying reactants, but organic chemists often use that, and that's because those are the materials you start with. Okay, so if we focus on what happened in this reaction, we did two things. First, well, and I'm not talking about chronological order, we just need to detail the two things that happened. We make a new carbon-carbon bond between carbon and CN, and then we also break the carbon iodide sigma bond. So that's what. Now we need to deal with the issue of how and in what order, okay? So there are sort of three mechanistic hypotheses you could come up with. And I'm going to use, there are three, two are more reasonable than the other. I'm going to start with the reasonable ones. I might skip the unreasonable one unless you demand that I don't. All right, so one possibility would be we break the carbon iodide sigma bond first, then we make the new carbon cyanide sigma bond second. All right, so now we're going to learn how to draw that scheme for how the reaction happens. By the way, the issue of how and in what order, the answer to this question of in what order and are bonds broken or formed, this is what we mean by a mechanism. Okay, mechanism answers the question, how, in what order are bonds broken and formed in a reaction? And we just proposed a mechanistic hypothesis, or a hypothesized mechanism, which is that we're going to break the carbon iodide bond first and then make the new carbon cyanide bond. So, starting with the carbon iodide bond, how would I show that breaking? Well, now we're going to use something you've already seen a little bit as we've dealt with resonance structures and a little bit with acid-base chemistry, but this is the arrow pushing part of a mechanism. We use curved arrows, and in my drawings they'll usually be red, to show bonds breaking or forming. And there's some rules you need to know for this process. So first, the arrow always begins with electrons. It must always begin either with electrons in a lone pair or electrons in a bond. Arrow never, ever, 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 ever starts with a nucleus. You never start with a proton or a carbon. You always start with electrons. So, if I want to show the bond breaking, I got to have my arrow begin with this bond between carbon and iodide. And the arrow always points to where the electrons end up. That's always going to be either a nucleus, if a bond is breaking, or the space between two nuclei if you're forming a bond. So in this case, we want to show the carbon iodide bond breaking. We'll simply draw an arrow like this that says iodide is leaving and taking its electrons with it. The lovely thing about mechanism is the arrows give you the instructions for drawing what the products of this step are, okay? I just showed that the carbon iodide bond was breaking and those electrons left with iodide. I'm going to color them red just to remind you that they used to be the electrons in that carbon iodide bond. If I'm following along and know about lone pairs, I see that iodide used to have 3 lone pairs and 1 bond. Now it has 4 lone pairs and no bond, so it has a negative formal charge. Yeah? Would it not just take one electron? What you're describing is another option, which I hadn't actually considered, which is one other mechanistic possibility is both partners lose an electron. Both partners take 1 electron from that bond. That is a possibility. That is called homolytic bond breaking. What I've shown you here is called heterolytic bond breaking. And for what we will talk about in chapters 7 and 8, it's almost always heterolytic bond breaking, whereas we're going to do a chapter on what's called radical chemistry, where things have unpaired electrons, and there it's going to be homolytic. So at this stage, I don't know that we're quite at the point where I could tell you why one is preferred versus the other. I think that'll become clear a little bit later. So hold on. Yeah. Okay, others? All right. So if I break the bond between carbon and iodide, what's left is still the methyl group, but that carbon, which used to be bonded to 4 things, is now only bonded to 3. And it stands to reason that if I took something neutral and something negatively charged left, the other partner's got to be positively charged, right? See, without knowing too much about chemistry, just some basic principles, you can sort of predict, if you see what the arrows are, you can predict what the products should be. Okay? All right. So that's one step of our mechanism. I said we were going to break the carbon iodide bond first. And the way this mechanism goes, the leaving group leaves first. And then, and notice that the methyl group that's left behind is positively charged. We call that a carbocation. This is what we are going to call an intermediate because it's a product of a reaction, but it's not the product of the overall reaction. We've taken one step, and now, in a second step, what we're saying is that the methyl group is going to react with Cn minus, and we're going to make a new bond between the Cn minus and the methyl group. The way that would happen is lone pair electrons on Cn minus would attack the positively charged carbon to make the new carbon cyanide bond, which I'll highlight in red. And there's our product. Okay, let's look at, so that's, see what we've drawn and see whether or not that agrees with what we said. First, break the Ci bond, then make the CCN bond. Yeah? All right, let's try to make some sense of those steps and see what's going on in terms of reactions and HOMO versus LUMO. The second step is the easiest to understand. Which is the nucleophile in this second step? Cn minus, good. You can tell because it's the one with the negative charge. We've said before that the HOMO of Cn minus is probably the lone pair on carbon. What about this carbocation, which is our electrophile? What's the LUMO on that carbocation? The unhybridized p orbital that's on the positively charged carbon. Okay, good. So really, one way to understand this mechanism is that the HOMO is attacking the LUMO. We're literally dumping electron density into that empty p orbital on the positively charged carbon of the carbocation. Take a non-bonding orbital on this partner and a non-bonding orbital on that partner, and we make a new sigma bond. HOMO and LUMO, by the way, is the key to understanding mechanism. It's the key to predicting mechanism. All right, because if you know what the HOMO of the nucleophile is and the LUMO of the electrophile, your mechanism will almost always involve HOMO of the nucleophile attacking LUMO of the electrophile. How about step 1? We've got a sigma bond and it's just breaking. We've talked about how to break sigma bonds before. Normally you dump electrons into an anti-bonding orbital, but here there's no nucleophile. It just sort of happens. How's that possible? One way to think of it is to remember, and you've maybe seen drawings like this before, on the y-axis is energy, on the x-axis is distance between two bonds. And there's a potential energy surface that describes how energy varies as the distance between two atoms changes. This minimum is at the radius, the average radius, say, for a carbon iodide bond. If you give the system enough kinetic energy, it can start rolling around this well and the bond changes length. If you give it enough kinetic energy, it can roll out to infinite distance. I tried to demonstrate this in my office once with one of you. I can't remember who it was, but it was hilarious because I'm like, oh, here's a spring. A bond is a spring. And I've got out my plastic slinky. And I said, if you stretch it long enough, and then at that exact moment the slinky broke, a bond can break, right? So that's exactly what's happening here. You have to give the system enough kinetic energy that you go uphill and the bond breaks. So I'm not sure my drawing there illustrates anything, but that does give you a sense for which of these two steps is slower versus quicker, right? Why do you think, if I told you that the first step was the slow step here, why do you think that's true? Go ahead.
Can I ask a question just based off that graph?
You don't want to answer my question? Fine, go ahead.
So, enough kinetic energy, it can go down and build that pump and then go off.
Yeah.
And that's how it breaks.
That's right. If you give it enough kinetic energy, then the bond, if you give the system enough kinetic energy, then the bond stretches to the point where one of the partners can escape. Okay, yeah, go ahead.
Can I answer your first?
Yeah, go ahead and answer my question, yeah.
I think that the first step will be slower because energy is required. And then after that, you have a nucleophile and an electrophile, and attacking that electrophile, it's in its nature.
Okay, so you're saying that the first step involves bond breaking. That ought to be uphill in energy. Okay. Whereas the second step involves bond formation, and you know that bond formation is generally downhill and releases energy. Right. So that it makes sense that the first step, going from the starting material to the intermediate, should be slow because you're just breaking a bond. And then also based on what I told you, somehow this system, the molecule has to acquire, just by one molecule bumping into others, has to acquire enough kinetic energy that the leaving group can leave, that you get over this hill and get to infinite distance. So you got to wait around for that to happen. But as soon as you form the carbocationic intermediate, yeah, you can have the nucleophile attack, and that's a bond forming step. So this now allows us to do something to sort of map out how we expect this reaction to work in terms of energy. If I draw what's called a reaction coordinate energy diagram with energy on my y-axis, and then on the x-axis, you're not going to like this because the x-axis isn't necessarily to be interpreted literally. We call it reaction coordinate. RXN is my abbreviation for reaction because I'm lazy. It doesn't save that much time, but there you go. Reaction coordinate, but it's basically a generic way to describe reaction progress. You might use as your reaction coordinate, say, the distance between carbon and iodide, and then you might switch after the iodide's left to use as a reaction coordinate the distance between carbon and carbon. But it's a way to measure how done the reaction is on a scale from not done to 100% done. Okay, so at sort of our zero starting point, we have our starting materials, and they start out at a certain energy level. Then we said in step 1, we go from starting materials to our carbocationic intermediate. That ought to be higher in energy, right? I'm going to zoom out a little bit and maybe give myself a little bit more space. All right, so we said that breaking the carbon iodide bond without doing anything else, this is my carbocationic intermediate, and that's higher in energy. And then we said that finally products, and if you go back up to the top of this page, we said that for this reaction, off the top of the other page, we said that this reaction was quite downhill in energy, and so that's why I'm showing the products at a lower energy level than the starting materials. Does that sort of make sense? All right, now let's describe the pathway that goes from starting materials to intermediates and then from intermediates to products. Along the way, it turns out anything we can observe, starting materials, products, or intermediates, are at local energy minima. And to get from one local energy minimum to another, you have to almost always go over a high energy peak. So there is a transition state between the starting materials and the carbocationic intermediate. And there is another transition state between the intermediate and the products. We're going to talk a lot about transition states, and we're going to talk about how to think clearly about the relative energies of transition states. Let's sort of put that off for a little bit, other than to say that in order to get from one valley to another, you have to climb a peak. Now, the way I've drawn this shows that the first step has to surmount a higher peak than the second step. You've maybe seen diagrams like this before. It's worth talking about briefly. The energy distance between the starting material and the first peak is called the activation energy for the first step. The energy difference between the intermediate and the second peak is going to be called the activation energy, which I'll call EA, energy of activation for step 2. You can see that the energy of activation for step 1 is much larger than the energy of activation for step 2. That's why step 1 is slower than step 2, okay? You've got to get over a bigger hill to go from starting material to the intermediate than you do going from intermediate to product. That is why this is the slow step and this is the fast step. You will have heard people perhaps refer to the slow step or the one with highest activation energy as the rate determining or even rate limiting step. I will abbreviate that as RDS pretty frequently. Okay? Questions so far? All right. Maybe we'll say briefly what these transition states would look like. I'm going to label this peak as TS for transition state 1 for step 1. This is TS2 for transition state for step 2. As I said, a transition state is a high energy peak that spans 2 valleys. Go ahead.
Just on the second, activation energy, since it's forming bonds, why do we need that energy in step?
If you're only forming bonds, why does energy go up a little bit? Usually, small energy changes like that are related to how the system has to change its geometry to accommodate what's happening. For example, while we're on step 2, let's just talk about that transition state. Do you notice that the carbocationic intermediate, I shouldn't have erased the positive charge, there it is. Do you notice that that carbon is sp2 hybridized and planar? And that those CH bonds are as far apart from each other as they can get. Notice that after that, the carbon is sp3 hybridized because now it's attached to 4 things. And these CH bonds are a little bit closer to each other. That means that in between these 2 intermediate and products, the geometry of that carbocation has to start distorting from planarity to be a little bit less planar and a little bit more tetrahedral. That happens as the bond is forming, but at least at the beginning, that generates some electron-electron repulsion between the CH bonds, and that's probably what's going on. And let me draw what I'm talking about in that transition state. Generally, we draw transition states in brackets with a double dagger, which is how organic chemists communicate that this isn't an intermediate, this is a high energy transition state. What I'm talking about is, as the nucleophile approaches, I'm using a dotted line to indicate that the nucleophile is still pretty far away from the carbon. The CH bonds have to sort of distort themselves a little bit from planarity. There's still going to be a partial positive on the carbon and a partial negative on the CN minus because this bond isn't completely formed yet. But what I'm saying is these CH bonds, as they approach each other, start to repel each other, their electrons do, and that's probably, to the extent that that happens before this bond is fully formed, that's probably some of the price you got to pay to get over the hill. Does that help a little bit? Okay. All right, so that would be sort of how our transition state for this reaction would happen. When you want to come up with a hypothesis for a transition state, you again use your homo-lumo intuition to know what's going to happen in the reaction, and then you try to draw something that's intermediate or rather in between your intermediate and your product. Okay? For the first reaction, the transition state for the first reaction, probably because the only thing that's changing in this reaction is the carbon iodide bond, probably the transition state looks a little bit like this, where the carbon iodide bond is sort of in the process of breaking, partial negative on the iodide because the bond isn't fully broken yet, partial positive on the carbon because the bond isn't fully broken yet. Geometry at carbon you would expect to be somewhere between tetrahedral and planar because again, you're in between. All right. So we've illustrated a potential mechanism for this reaction. We've discussed how the first step is probably the slow step. And we've discussed why the second step is faster. Now, I've told you that first step is a rate determining step. That means it's the only step that matters in terms of setting the rate. The second step is so fast that the rate of the reaction is determined entirely by the slow step. The analogy here was years ago, my family were making a ton of sandwiches for some purpose, and I'm forgetting whose assignment was what, but it became clear that one of my sons was the rate determining step, that it did not matter how fast the other son bagged up the sandwiches if the peanut butter spreading was too slow. The only thing that mattered was the peanut butter spreading, right? So in the same way for this reaction, once you've identified the rate determining step, that's the only one that matters for how fast the reaction goes. So this allows us to do something called writing a rate law. And once you've identified a mechanism like this, and once you've chosen what the rate determining step is, which I will star, the way you write a rate law is to say that the rate depends on some constant K times the concentrations of each molecule that is involved in the rate determining step. So in this case, there's only one molecule involved in the rate determining step, and that is the electrophile, the methyl iodide. In other words, if you were to plot the rate of this reaction versus the concentration of methyl iodide, and you can do these kinds of experiments, what you would see is basically a linear relationship between concentration and rate. We would say that this reaction is first order in methyl iodide, and that would tell us that there is one and only one molecule of methyl iodide involved in the rate determining step. That may be somewhat familiar to you from 106, or if you maybe have some vague recollection of something similar to that. Yeah, ish? Okay. If you don't, you'll want to read carefully in chapter 6 and 7 because it's going to help you a lot with that. Now, the fact that Cn minus is not involved in the rate determining step tells us that if you were to do an experiment with Cn minus and vary the concentration of Cn minus over some range, increasing the concentration of Cn minus would get you nothing in terms of rate. All right? So this reaction the rate of this reaction mechanism would only depend on the concentration of methyl iodide. We would say that it is 0 order in Cn minus. Alternatively, you could say that the rate is independent of Cn minus. All right. Periodically, people ask the question, how is it possible that the rate is independent of Cn minus? Because the reaction involves Cn minus, and if I have no Cn minus present at all, the reaction doesn't happen. And I say, you're absolutely right. At really, really low concentrations of Cn minus, the rate law gets more complicated. If you want to see the full derivation, I would love to show it to you. You can come to my office, or better yet, you can register for Chemistry 552, which is offered in fall, and we will talk about these issues exhaustively. Nobody's ever taken me up on that. So, all right. Because this mechanism only has one molecule in the rate law, we call this a unimolecular mechanism. And mechan, how do you spell? Yeah, drop the S, silent S that shouldn't be there. Unimolecular mechanism. This reaction mechanism that we've proposed is a substitution mechanism, and it involves a nucleophile attacking an electrophile. So we call this reaction unimolecular nucleophilic substitution. And because we don't like to say words when we can say abbreviations, we're going to call this SN1. And that word will become, that series of letters will become the bane of your existence along with a series of other letters. SN1 is a mechanistic hypothesis for a reaction. Now, that's just one. And I'm going to be, right now we're being totally agnostic as to what the actual mechanism of the reaction is. We're just generating hypotheses. And frankly, we've got a pretty good hypothesis that we can run into the lab and test. We just vary the concentration of starting materials, and we see how the rate depends on the concentration of those starting materials. If we ran into the lab and we found that the rate was linear in methyl iodide, but was not 0 order in Cn minus, or rather was maybe linear in Cn minus, that would tell us something. It would tell us that this mechanistic hypothesis was wrong, right? And this is how organic chemists learn how reactions happen. I want to show you now mechanistic hypothesis 2, and it's simpler than what we've just done. because mechanistic hypothesis 2 is going to be, we're going to break the carbon iodide sigma bond and make the new carbon CN sigma bond at the same time in the same step. Okay? Yes?
Just make sure I understand. You can never have 5 bonds on a carbon.
Right, you can never have 5 bonds on a carbon because, and that's the question I was anticipating, that's mechanistic hypothesis 3, can we make the bond first and then break the other one? That would involve an intermediate with 5 bonds to carbon. Carbon is small enough that it gets hard to make 5 bonds and have them all be stable. And so other elements that are bigger than carbon, sulfur, phosphorus, can have 5 bonds, that's just fine. But for second row elements, no more than 4 bonds. Yeah. So we're ruling out mechanistic hypothesis 3, which is you make the CCN bond first and then you break the iodide bond, simply because it would involve 5 bonds to carbon, and based on experience, we know that that's not reasonable. Yeah. All right, mechanistic hypothesis 2, break and form at the same time. So what would this look like? I'm going to draw methyl iodide again. I'm going to draw our nucleophile. Breaking the bond would look like carbon iodine bond leaving, just like we did previously in the first step of that SN1 mechanism. Making the carbon cyanide bond would simply involve an arrow from the lone pair on cyanide to the carbon. We're showing those 2 arrows in the same step, communicating that the bond breaking and the forming are happening at the same time. The product is going to be iodide having left, that's our leaving group. And then CN having come in on the other side. If we were to draw the transition state for this reaction, we would predict that we would draw a dotted line for the carbon iodide bond breaking with a partial negative on iodide, and then another dotted line for the CN minus bond forming with a partial negative on CN minus, because the bond is partially forming. And then we would show some intermediate geometry where the carbon, because you're breaking a bond on one side and making a bond on the other side, you sort of go through an intermediate where or you go through this transition state where as the nucleophile approaches from the left and the leaving group leaves to the right, the carbon hydrogen bonds have to sort of invert away from the incoming nucleophile. You go through some intermediate where it almost looks like that carbon is planar and sort of sp2 hybridized. And then as you go through and make the new bond with the nucleophile, it's like an umbrella inverting and the CH bonds pop over to the right side. Okay. When we return, we will talk about what's going on here with HOMO and LUMO. We'll draw an energy diagram, we'll make rate law predictions, we'll name this reaction mechanism. All right, see you on Friday.